Welcome back, nerds. Alrighty. Section 1.2. Yes, every day, nerds. Section 1.2 is where we are now in AP Precalculus, functions and their properties. Going to start with some Algebra 1 review, domain, range, and functions. The domain of a function is all of the x's that are allowed to be used for that function, all of the x's that exist for it. The domain is what we would call the inputs. The range of a function is all of the outputs, the y values that are associated with their corresponding x values. And what does it mean to be a function? A function is any relation that has exactly one y for each x. So for every x, there's exactly one y. That's what it means to be a function. And the way that I can help you remember that is, think about a four-function calculator, right? It's got add, subtract, multiply, divide, right? Four-function. It's got the word function in it. If you took a calculator and you typed 1 plus 7, you expect that calculator to tell you 8, correct? And no matter how many times you type in the input 1 plus 7, you expect the output to stay the same, 8. Could you imagine if you typed 1 plus 7 and the calculator said 8 sometimes and other times it said like 5? You would immediately say that calculator is broken. Not because it can't add, but because it gives you different answers for the same input, which doesn't make any sense at all. It's not a function if you can get two different outputs from one input. However, getting the same output from multiple inputs, that's not a big deal. 1 plus 7 is 8, but so is 3 plus 5. Okay? So what we have here in this abstract image is we're imagining a domain of a function being 4 different x values in a space, this bean-shaped thing, and we have arrows leaving each of those x's. Every x has exactly one arrow that leaves it. Therefore, we know it's a function. But Mr. M, what's up with this y3 having 2 different arrows point to it? That is like 1 plus 7 and 5 plus 3. 2 different inputs, but they give me the same output. Whatever, that doesn't matter. That function's still working. That calculator is not broken. Make sense? You can only have one output per input. Here, this one does not represent a function, because right there at x1, our calculator gives us 2 different answers for the same input. Sometimes it says 1 plus 7 is 8. Other times it says 1 plus 7 is, 5. This calculator is broken. That is not a function. Can't do that. So if you ever have an x that points to 2 different y's, you don't have a function. Cool? All right. So we come down here and we look at these images. I think we talked about this already. Did we talk about that these are images from a graphing calculator screen? No, we didn't? Okay. As I use the same question in Algebra 2 Honors as well when I introduce functions and stuff. So these grids have no numbers on them because they are literally graphing calculator screens. That's what you're looking at. And the brackets down below are telling you the size of the window. So this says my x-axis goes from negative 4.7 to positive 4.7, and my y-axis goes from negative 3.3 to positive 3.3. So that's how you read that image. Cool? All right. So we have 3 different graphs here. And I'm looking for, this is a small class. There's only 26 of you. I'm looking for 26 voices when I ask if this is a function, and the answer is either yes or no. And I'm hoping to hear lots of the same answer. So class, is this a function? Yes, it is. One of the ways that we know is it passes the good old vertical line test. And the reason why we use the vertical line test is because if you draw a vertical line, it goes through a single, it goes through a single x value, which means for that x, there can only be one y. So because it passes the vertical line test, yeah boy, that is a function. As a class, Is this a function? Yes, it is. Once again, we've got a graph that no matter what vertical line I draw is only going to touch this graph one time. And lastly, as a class, is this piece of spaghetti a function? No, it's not. This one's going to fail the vertical line test. I can't spell fail. I failed it. Spelling fail. Fails the vertical line test. Just as an example, I'll draw one somewhere that hits the graph more than once. And because it hits the graph more than once, we have an x that points to more than one y. That calculator's broken. Pretty easy though, right? Cool. Alrighty. AP Pre-Calc is pretty big on something called change in tandem. And it's going to pop up in tons of sections. Change in tandem is what they're calling describing rates of change and how they're related to one another. Because in tandem means together. So we're talking about how things are changing together. What we have here is Rosina making $16 per hour at her job. You see, because I had to say per something, this is a rate. Rosina makes $16 per hour at her job. If she works more hours, she makes more money. You see, the amount of money she's making is also changing. So that's what we're talking about, change in tandem. When one changes, the other one changes. And hopefully that makes sense. So the number of hours you work changes. The amount of money you make changes. It's pretty obvious. If she works 2 more hours, and I'm looking for hands because I'm trying to learn names, what will be the change in her week's pay? Adi?
She'll get $32 more.
She will earn $32 more, and I might as well write in green since we're talking money. It was very, very easy, but it's 16 times 2. She worked 2 more hours, so she earned an extra $32. AP requires that you use units. And if you don't use units, you will lose a part of the score for that question. So I use the dollar symbol. Easy enough. What tends to be a little bit more of a challenge for my students and students in general, not just mine, is figuring out what the domain of a function is without its graph. So algebraic. Notice I didn't say range. We really don't do ranges all that often without using technology. But domain we should be able to do by hand algebraically. Sometimes I try to find range by hand because I'm a nerd and I'm just curious. But domain. Here we have a square root function. Square roots have a very specific rule about what you can and cannot take the square root of. Looking for hands because I'm trying to learn names. Other than Adi, I appreciate you. But can someone tell me the rule? I forgot your name. What's your name?
Martin.
What is it?
Martin.
Martin, can you tell me what you know about square roots? What's the rule for square roots in general?
It can't be a negative number.
Where?
Positive.
Where?
Inside the...
Inside it, right. So we cannot take the square root of a negative number. Just so you know, the inside of a square root is called its radicand with a D at the end. But another terminology that you can use that I actually prefer because it works for tons of different kinds of functions is called the argument. The argument is whatever had operations acting on it. So I can say the argument of a radical, I can say the argument of a logarithm, the argument of an exponential, the argument of trigonometry. It means the stuff inside. That's basically what that means. So we know that the argument of square root, he said, can't be negative. So if it can't be negative, what can it be? Positive and 0. Because you can take the square root of 0. It's 0. So the way you find the domain of a square root function is you grab its argument, its radicand, and you set it greater than or equal to 0. This guarantees no negatives. And then you solve for x. I don't have a whole lot of vertical space, so I'm going to scoot to the right. And a lot of times this is an acceptable answer. But we being AP students and teacher, are going to use interval notation instead of inequality. Hopefully everybody's comfortable with interval notation from Algebra 2 Honors last year. When you describe all numbers at or greater than -3, you say domain, colon, -3 with a bracket, and then never stopping, so climbing all the way up to positive infinity. You can never bracket an infinity because it's not a number. You can't reach it. It's a goal. You'll never get there, though. Is everybody comfortable with interval notation, brackets, and parentheses for equal to bars or not? Inclusive, non-inclusive? If not, ask, please. Yes, ma'am.
So why did you make it an inequality?
Why did I do interval notation?
No,
Here? Just to help me solve for what the domain is in case it wasn't easily seen.
and that probably was the square root thing. Oh, okay.
Yeah, so basically, because x plus 3 was inside the square root, I knew it couldn't be negative. So we go, well, how do I figure out what would have made it negative, quote unquote? So you go, okay, well, greater than or equal to 0, and solve. So for one like this, it's pretty simplistic to see it. But what if it's not so easy in there? What if there's a quadratic inside the square root bar? Completely changes the question. And then we're happy we're doing it this way. But that's why. Oh, my phone's not on vibrate. There will forever be YouTube proof that I didn't do my job, put my phone on vibrate. There we go. Okay. Next. In part B, we do have another square root bar. So the square root bar is going to play a part of this domain. We've already discussed it. The argument of the square root, this time just x, better be greater than or equal to 0. Well, that one's pretty easy. For the top numerator, we know that x is greater than or equal to 0. I'm not going to write it as an interval yet because we're not finished. But there's more going on here than just a square root bar. There's also a fraction. Fractions come with their own rule. One very specific rule. And I got the same couple people, but I'm still trying to learn names. So I have new volunteer that can tell me what they think the one rule is, the one thing you have to remember with fractions. What's your name?
Kate,
Kate, what do you got for me?
the denominator can't be 0.
The denominator cannot be 0. You're not allowed to divide by 0. We don't know how big 0 is. We don't know how many zeros fit into things. So we treat it as an equation, inequality, and just get x by itself by adding 5 to both sides. And what we find out here is that we have a restriction on our x's. We cannot use the number 5. So we have two different rules. We have that x must be greater than or equal to 0, but x also can't be 5. And both rules have to be abided by. So the question becomes, how do we set up an interval that says all the numbers greater than or equal to 0 except for 5? Just in case we're not sure, I'm going to go ahead and spell this one out. He said the word, but we're going to need to use a union. There's going to be more than one interval. Our domain will begin at and include 0. It will climb up towards 5, but cannot include it. And then we use for the math symbol, that means, oh, also this stuff too. The union. Starting at 5 and never stopping again. So the union symbol is basically how we hop over numbers that we can't include. Questions, comments, concerns on the answer for that one in interval notation? Or it's pretty easy. Makes a lot of sense. Fingers crossed. Don't be afraid to ask. Okay. This last one has an x squared in it. Good news. You can square anything. There's not a single number in the known universe that you can't square. But the domain of this is not all real numbers. Because it's a real world problem. It says that a of x is the area of an equilateral triangle that has side lengths of x. So imagine you got a triangle. You can see that all of its lengths have X on them. Because it's a real question, there is a single restriction about that X. Okay, Adi, what do you think?
It can't be negative or zero.
It can't be negative or zero. Literally, if it's a real object, the only rule is the length better be a positive number. So we go, X has to be greater than or equal to 0. Like that's it. As an inequality, but as an interval, that domain would say 0 to infinity. Ta-da. Yes, ma'am. No, I can include. Oh, crud. I did man. I know, right? It's too bad I don't know how to edit videos. I would totally cut that out. Anyway, he said can't be negative or 0. It's a good thing you guys are smart. There we go.
With negative 3 and infinity,
Yeah.
how would it be equal to if it can't be negative 3? Can it?
This one can be, because this says you can begin at negative 3 and go larger. So let's check it out. Let's take X equals negative 3. If you throw a negative 3 right there, what you get on the inside of this square root bar is a 0. And the square root of 0 is 0. So that's allowed. As long as it's not in the bottom of a fraction, because you know the bottom of a fraction can't be 0. So like this question, if you turn it upside down, it has a different domain, which is neat. Because things being on the top of a fraction or bottom of a fraction mean different stuff. But yeah, that's why, because I could take the square root of 0. Yeah.
Where did we get the 0?
It's 0 because this is a real object. So if I handed you a triangle and said measure the sides, they could literally be any number as long as it was positive.
Oh, so it can be 0 for like any.
It can't be 0.
Yeah.
Yeah, because if it was 0, you didn't have a shape. That's why. It can be the world's tiniest triangle, you know, but it can't be 0 side. Now, you don't need your graphing calculator for this one because I'm going to show you on mine. It just says use a graphing calculator to find the range. As long as you know how to graph anything on a graphing calculator, you're fine. I'll tell you when you need your graphing calculators for new skills. Today is not a new skill because we graphed things yesterday. We go to y equals, and you can see that I already have 2 over x ready to rock and roll for us. And that's its graph. Sir? The stack fraction. So if the operating system on the graphing calculator is new enough, the shortcut for it is alpha, and then y equals. And if a menu pops up, it'll say n over d is number 1. You just hit enter, and now you have stack fraction. 2 over x, and then it'll regraph that for me. Now remember that the graphing calculator it's shading pixels, right? It's like Minecraft, nothing's round here. Everything is straight things. I know that over here it kind of looks like it touched the x-axis, but it didn't. And it never can. Because think about it. There is a single x that you're never allowed to use. What x value is that? Can't use 0. Well, that's this vertical asymptote. But you'll never get y equals 0 either. Because 2 is a positive number. And you can divide it by anything you want. Except for 0. So 2 over any number other than 0 will never equal 0. It's not possible. So what we're seeing here is a graph that goes up and down forever. So it hits every single y value except for 0. We know that y cannot be 0. So how do we write that in integer notation? Once again, a union. Anytime you have to hop over a single value, you use a union. So you say the range is negative infinity up to 0, but don't include it. Throw union, math speako, also this stuff, 0 to positive infinity. And there it is. Not bad, right? As long as you don't have to do it by hand. You got a picture to look at. Okay. On to a concept that It annoys me that it's part of the curriculum, to be honest with you, because I feel that you can't have a very good understanding of what it is you're saying without some calculus knowledge. But we're going to do our best to get cute with the definition like our authors do. I'm going to talk about continuity. The old textbook says a graph is said to be continuous if it has no breaks in it. It's smooth. It's a smooth, uninterrupted curve. The new book amended that definition a little bit and instead said that there was no, what was the exact word? It didn't say no breaks. It says, see, this is bad videos. I wasn't ready to say this again. I read it earlier. Man. Well, I can tell you what it does. It gets cute with the word, and instead of talking about the graph itself, it talks about at specific points only. So that's what we're going to do. We're going to talk about continuous at specific x values, not whether or not the graph is continuous. It's completely different. You'll learn more about that in calculus. Instead, what we're going to talk about is it continuous at that point? So here, since this curve is a smooth, uninterrupted curve at every x that we can see, we can say it is continuous at every x that we can see. Whereas this one, at the value x equals a, our graph is not continuous. Literally, this whole section of the graph, starting here, just broke off and went up to get you to here. We call it a jump discontinuity because it appears as though an entire piece of the graph has jumped up or down. Okay? You will have test questions from me where you're going to look at an image and I'm going to say what kind of discontinuity is between these two x's, and you would just identify it. You'd be like, oh, that's a jump discontinuity. That easy. Now, these next two are two different versions of the same kind of discontinuity. They are both called removable discontinuities. And I like this one is a prime example of removable discontinuity because it is literally a hole in the graph. A point has been removed. This one has been removed and then placed somewhere else vertically. Why is this not a jump discontinuity then, might be the question. Because it was not an entire span of the graph. It's a single point in space. So if a single point in space is either missing or a single point in space has moved, we say that this is a removable discontinuity at that point. Yes, Adi?
Why wouldn't you just draw the line up to that point and back down?
Because it would be vertical. And we can't, and if it's vertical, then it's not a function. Good? And this last one we just encountered on our graph. Here the graph shoots up to infinity. Here the graph shoots down to negative infinity. And that is why at vertical asymptotes, we call this an infinite discontinuity because the graph heads to one or both of the infinities. So if a graph heads to one or both of the infinities at an x value, that x value is an infinite discontinuity. All vertical asymptotes are called infinite discontinuities. Okay? So you have three kinds of discontinuities that you need to worry about. Jumps, removables, and infinite. You just need to know what they look like. So we look at these three graphs, and we're asking the same question at all three of them. Is there a discontinuity at x equals 2? And if the answer is yes, what kind? So looking for 26 voices. In example A, is there a discontinuity at x equals 2? Yes, there is. What kind? Infinite. Yep, there's a vertical asymptote at x equals 2. So we have an infinite discontinuity there. Here is x equals 2. So as a class, does it have a discontinuity there? No, it's continuous at x equals 2. And lastly, here, does this graph have a discontinuity at x equals 2? Yes, it does. I'm getting less voices. What kind? Removable. There's a hole in my graph. All right, removable discontinuity at x equals 2. And there it is. I have enough time to explain the next concept, and that is where the video will come to an end. Talking about intervals of increasing and decreasing. Now, depending on who you had for Algebra 2 honors, you may or may not have learned this last year. I'm not trying to insult any intelligence. I like to break things down. When we read a book in English, we read from left to right. When we count from small to big. And on a number line, that is left to right. So because of that, I'm going to ask that you read your graphs from left to right. And I like to tell people, pretend it's a roller coaster track. And as you went from left to right, what did your roller coaster car have to do? If it had to go up, that is where your graph is increasing. If it had to go down, that is where your graph is decreasing. And if it was just flat, straight across, that's where your graph is constant. So this has a roller coaster car that would be forced to go up. Here's you. Okay? Be forced to go up as you rode this roller coaster to the right. Mr. M, isn't it getting flat over here, therefore constant? Well, it may be approaching a horizontal asymptote, but technically, it'll never get there. It will continue to get closer to it for all eternity, which means it's technically still going up for all eternity. It'll just never get to the value it was trying to get to. So that one's increasing. This one, if we let the roller coaster car go from left to right, here's you again. You're going down, so you're decreasing. I should have written we. Oh, that would have been so much more fun. Anyway, there you are. This is perfectly horizontal. Slope of 0, therefore constant. In all actuality, increasing means at this point, my graph has a positive slope. Decreasing means at this point, my graph has a negative slope. Constant means at this point, my graph is flat. Okay? And then here, we hope this is never the shape of a roller coaster track because I don't think very good things would happen right here. But, there it is. From here to here, on that interval, from negative infinity to negative 2, you're decreasing, negative slopes. But from negative 2 to positive 2, constant because horizontal. And then after 2, increasing. One thing I do want to point out, though, AP has decided, I'm assuming because of shifts in mathematics in recent years, that at zones where a graph changes from increasing and decreasing and constant to something else, we use brackets. When I was in school, you would never put a bracket there or there. Because right there, how can I say that this point is both decreasing and constant at the same time? But that is the definition that AP is now using, so we have to get used to that. Some of you are probably already used to that because of the Algebra 2 honors teacher you had, because they also teach AP Calculus. But just want you to know, when you change between increasing, decreasing, and constant, you will use brackets. And we'll go ahead and do some examples of that tomorrow because we have to actually look at the graph itself. For now, that's it, nerds.